Let's talk about addiction. But we're not going to talk about it as a moral failure or, a lack of willpower. We're going to deconstruct it as something much more fundamental, a predictable, even an exploitable error in your brain's own learning code. And to understand this bug, we first have to reverse engineer the original program.
So, our whole investigation really kicks off with a puzzle. How can a drug, a medicine like L-Dopa, that's designed to help people with Parkinson's disease, how can that sometimes create a devastating impulse control problem, like a sudden, all-consuming addiction to gambling? To solve that, we've really got to look under the hood at the brain's core operating system. All right, Section 1, the learning algorithm. Before we can even get into the glitch, we have to appreciate just how elegant the original code is. This is the learning algorithm that your brain is running constantly, every single second, to help you figure out the world.
Okay, so at the very heart of all this is a concept called reward prediction error, or RPE. You can think of it as the brain's fundamental algorithm for learning from experience. It's a really simple signal, and it's encoded by dopamine. And it's basically just asking one question, over and over and over. Was that result better than I predicted? Was it worse? Or was it exactly what I thought would happen?
So let's break down how this actually works. It's super simple. Let's say you expect to get one cookie, but you actually get two. Well, that's a positive error. Reality was better than your expectation. Your brain gets a burst of dopamine that basically screams, hey, whatever you just did, do that again. But if you expect a cookie and get nothing, that's a negative error. Dopamine levels dip, signaling disappointment and telling you, yeah, maybe don't do that next time. And if you get exactly one cookie, just like you predicted, dopamine stays flat. No surprise, so no update to the code is needed. This is literally how we learn everything, from tying our shoes to really complex stuff.
So now we've got this really elegant learning algorithm. But just like any piece of software, it has vulnerabilities. And now we get to the exploit. This is how you corrupt the system's training data.
And the hacking agent in our story is L-Dopa. What is it? Well, it's a molecule that the body converts directly into dopamine. For Parkinson's patients who don't have enough dopamine, this is a lifesaver. But the side effect is that it can create this massive, totally unnatural flood of dopamine that the brain is just not equipped to handle.
And we're not talking about a subtle change here. Researchers like Kenneth Bloom have pointed out that this flood can cause something called hyperdopaminergia. Basically, an excessive, disruptive tsunami of dopamine that throws the brain's finely tuned chemistry completely out of whack.
And here is the crucial hack. This flood of L-Dopa completely hijacks the reward prediction error algorithm. It creates a constant artificial positive error. The brain's code is now being fed garbage data. It's being tricked into thinking that reality is always better than expected, no matter what actually happens. The surprise signal is no longer a signal at all. It's just noise.
Okay, Section 3, corrupted output. So what happens when you feed a learning algorithm corrupted data? Well, you get a corrupted output. This is where the bug in the code starts to show up in some really devastating real-world behaviors.
And the real-world impact is pretty stark. Studies show that up to 17%, that's almost 1 in 5, of Parkinson's patients taking these dopamine-boosting drugs develop what are called impulse control disorders. We're talking about things like pathological gambling, compulsive shopping, behaviors that show the learning algorithm has just gone completely haywire. To really understand why this happens, we have to look at this critical distinction the brain makes, a distinction that this hack just completely shatters. This really gets to the core of how addiction works. The system separates liking something from wanting it. So on one hand, you've got liking. This is the actual pleasure you get from something, that warm feeling of a win, the taste of good food. And for the most part, this system stays intact. But on the other hand, you have wanting. In neuroscience, they call this incentive salience. It's not the pleasure itself, it's the magnetic pull that an action or a cue has on your attention. It's the drive, the compulsion to go after a reward. And this is the system that gets hijacked by that constant, fake, positive error signal. And the result is a catastrophic error in the learning process. The algorithm stops connecting the action to the pleasure of the reward. Instead, it learns to pathologically want the pursuit itself. The addiction is no longer about the feeling of winning at the slot machine, it's about the act of pulling the lever, over and over. The motivation has become completely untethered from the actual outcome. So this all builds to the final and most devastating consequence of this hack, a corrupted, self-perpetuating, infinite loop in the brain's code. At this point, the whole system is fundamentally broken. The brain starts assigning massive importance, that salience we talked about, to any cue associated with the behavior. The lights of the casino, the sound of the machine, those things become incredibly powerful.
The actual win or loss, it almost becomes irrelevant. The compulsion to just keep going is all that matters. And every single time the action is repeated, it reinforces the desire to do it again. It's a vicious, inescapable cycle.
You know, if we were to actually write this out as a piece of computer code, it would look something like this. A simple while loop. While the cues for pursuit are present, seek the reward. But the hack has broken the exit condition. That artificial flood of dopamine ensures the condition is always true, so the loop just never terminates. It's a bug in the code that traps the user in a compulsive, repetitive behavior that has no off switch.
So this reframes our entire way of thinking about addiction, right? It's not a failure of character, it's a failure of code. And that leaves us with a really powerful final question. If addiction really is a predictable learning error, a bug caused by a data hack, then can we stop just trying to treat the symptoms and actually learn how to debug the brain?